Yes. That was the only video that had this trouble, right? About the audio issue. There was only one video.
One of the video.
So there is a homework 6 due. It's Tuesday. So we will have 2 classes between them, so today and Monday. So hopefully, okay. Um, So there are only 2 midterm exams. The next is final. Question?
Yeah, actually, it was in regards to the midterm. I have a doctor's appointment that day that I can't
Okay.
really miss, and it's very difficult to reschedule.
Can you guys talk to each other? I think it's
Yeah.
primarily Rob that, because before he takes a holiday for that, that should be fine. Can you guys talk to each other and
Yeah.
get me a reasonable thing that suits everyone? Yes, like we are only 4 people. This can be
Okay.
easily accommodated. Unless someone else comes and says that, no. For example, if Rob has already taken a leave, then there is a priority issue. Then I'll stick to this,
Right.
like whatever is official. But I think if you catch Rob ahead of time, he probably has not done it to my knowledge.
Okay.
Okay, is that reasonable?
Yeah, I'll talk to them.
Yeah. Yeah, I am perfectly fine with changing, even if in the worst case, he has already fixed it, then let's find a way out. It should be possible to. I don't think I can make an exact exam if that's hard. Like it takes some effort to make an exam. Like if I make a makeup exam, I don't give so much thought on it. Like I just pick random questions and do it. So it's not a good exam. Right, so yeah, first talk to Rob and then get back to me and we'll go from there.
Sounds good.
About the other midterm 1 exam, here are the grades. So it's only 4 people. If I list them, it's kind of so this is after midterm homework, everything is a total, right? And this is 1977 and 76. The grades in the quiz is 1.00, like that's full score, and there's 0.88. I think 2 single digits in these is okay. And this leads to a curve. So what I did was I gave back 15% of whatever you lost. Remember the scale? So what I do is that if you score 80, plus in principle, I can return back all of what you lost. 100 minus 80, that will make a full score. I give back a percentage of it. So I give back 15% in this case that I decide, but not on very personal basis for the whole class. I do that. So 15% of this is returned back. But then if you need to get back, you need to get full score in a quiz. So that's where the quiz becomes important. If by any chance you're not submitted any quiz, then this is your score. It happens. There are semesters that I've had students who don't submit a single quiz. Then whatever you earn is what you get, right? So that's 0, then you don't get back. But typically, most 99% 90% of the students try to utilize this. So for me, it is just the idea that that means you're trying at home. And I, at least in this course, I try to give weightage for just trying. Like even if you're thinking, and that's the whole idea of quiz, that okay, my feeling is that you're gonna thought over it. You don't have to write everything. If you just say that something, from my perspective, even if it is 2 minutes, you have at least given some thought on the course. So that's fine. Very vague, not very personal, but that's all it is. So it's very clear. So in that sense, quiz is weighted a little more than what it is actually showing up on the grade.
Yeah.
Any questions on that? Right. And what I might do is, let's see, since Tuesday, the submissions have switched to Tuesday, I'm having real difficulty following your quizzes. Like some of you write the quiz date, some of you don't write. So often it is hard for me to remember which quiz date are we talking about. And I understand that you guys don't like it. So what I might do is that I will start making it due on D2L. Like last year, that's what I did. So on D2L, you'll have to just take a picture and submit. Is that clear what I mean? Like especially for Abhiyan and Johnny, right? So it will be due on D2L. That'll be due date. It's the same as this. It's probably convenient in the sense that you take a picture. It's a little inconvenient for me that you got to go and grade it, but it's better than I'm completely getting lost at this point. Some of you guys attach it to the homework. I don't see it until I grade the homework. And before that, I have given a 0 there because I didn't find it. So it's getting a little confusing on my end because there is no systematic way of submission, even though it is only 4 students. Believe it or not, I'm getting confused. So is that clear? So I will have it on due on D2L. But homework is still the usual. I like the homework in a physical format. I prefer that, even at the price of not getting organized. The quizzes, I think, because there are more number of quizzes, probably that's why it is more confusing. Okay. Okay. Come on, move. So, oh yeah, before that, we want to talk about that analyticity along, no, the derivative along an x equal to y line, right? So let's talk about f of z is equal to z squared. That's a decent, I think that's what we were doing, correct? Yeah. So, so we go along this line, and this is 45 degrees then. X equal to y is 45 degrees. So this is x, this is y. That means the real part of z is a complex plane. So let's say z is equal to x plus iy. And delta z now, we have to choose. So this is somewhere along at this point could be your z. That's your z. Correct? An arbitrary point out there. Now I choose to go anywhere around z. I have to find a close point, but I choose a line parallel to this. So that's fine. dz. Is that clear? So delta z that way is a small element to the right, delta x plus I delta y, but in such a way that delta x is exactly equal to delta y, and it is greater than 0. Possibility that you're going in the first quadrant along x equal to y, and that's it, I suppose. Yeah, so how about this? So this is equal to delta x plus I delta x. That's the condition we have put. That's pretty much what it is. Since I'm going an arbitrary distance, it's also convenient to divide this by 1/√2. That way your magnitude is 1, but you don't have to. Right, this is good enough. Is that clear? So this is your delta z. From this point on, you proceed and so this is 1 plus I times delta x. And now we do derivative of z. That's equal to, and that's equal to limit of delta z tends to 0. That means delta x tends to 0. So that's z plus delta z, which is 1 plus I delta x square minus z square divided by delta z. This is 1 plus I times delta x. So, okay. And now you subtract things as much as you can.
You are not dividing it into real and imaginary part. I mean, does that?
What's the question?
I mean, does it into 1 plus I del x? In generally, for left hand side and right hand side rule, we use the real axis and imaginary axis.
Yeah.
But in this problem, you are not using the separating the real and imaginary part.
When do I do the real and imaginary part?
I mean, in one part, I del x tends to 0. And another part,
1 plus times delta x tends to 0. Yes.
Yeah.
But that's okay, right? So is that the question? Like, so how can this and this together go to 0? It's okay, right? If you have one variable, yeah, so this is in such a way that as you're coming in, the imaginary part also goes to 0, real part also goes to 0. Correct? If you're, I think I'm not getting the question maybe. So as you go along this line, the real part is going down, imaginary part is also going down, right? That's the way it is designed along that line. Is that the question?
Yeah.
Sure?
Yeah.
Okay. Okay. Yeah. Right.
Yeah, okay.
Or maybe I didn't get the complete picture of the confusion.
Okay, go on. I will ask later.
Yeah, ask again here. Okay, question? Okay, no, okay. So it's so at this point I just expand on this, and delta z going to 0. Now we said just now that there's only one variable, so it's delta x going to 0. The same. So it's delta x going to 0. And then I expand this out, z square cancels, and that is a 2 times 1 plus I delta x. And then there is plus 1 plus I the whole square times delta x squared. Since it's a simple function, there is only 2 pieces, otherwise there's a whole series out there, and divided by delta x. And oh no, 1 plus I also, 1 plus I. And again, these cancel out nicely, and this is equal to limit delta x tends to 0 of 2 times what happens to the z? Oh, here there's a z also,
We
right?
cancel it.
Yeah, yeah. Z.
Oh, and there again.
So it's a z there. So it's 2 times z plus 1 plus I the whole square. No, 1 plus I cancels out, and then I have that. But this goes to 0 all the time. So that's equal to 2 times z. In fact, that tells you this should, I mean, this way of writing it sort of tells you that any line actually, if you give me the slope of this line, so this is any line, right? Y is equal to mx. Right? So I can actually write this in general, this will be delta x and m times delta y, right? So this will be I times m. That's it. So for L along any line, I just have to put a M everywhere. They will always cancel out. Along any line. Yes.
Is this like restricted to linear? So, I mean, can you have a quadratic X?
Yes, in principle, you can have a path which is quadratic. Yes, that should also work out. I haven't done it, but you want to experiment that now. Let's see. Yeah, so then you would say delta y. Yeah, let me think. Good point. So you make a change along a path, right? I can make a change along any path I want. Okay, I think it will work. Let's diagram, but and I don't have an answer as such. I think it should work. Just conceptually speaking, if you're going along a path, it should work, but there might be some challenges as far as algebra is. That's it. Okay, the same thing, and we are saying that delta z is equal to delta x plus I delta y. But delta y is not independent of delta x. Instead, you say that delta y is a quadratic equation will be, let's say, alpha times delta z squared, sorry, delta x squared. That's what you mean?
Mhm.
It's some
Yeah.
arbitrary parabolic form, right? So that's equal to delta x. Yeah, it should work, I think. Yeah, so delta x times 1 plus I times alpha times delta x. See, here you can immediately see what's happening. In the limit delta x tends to 0, this is small. I can drop it here itself. But if you want, you can keep going through. Like right here, this is a higher variation
Right.
than this, so I can drop this right here. But if you keep it, right, so then you will say df by dz, that doesn't work. So this is limit delta x tends to 0, right? So this is z plus delta x. You know, now this is already a bigger number than the next number. This will always be bigger than this. Is that clear what I'm saying? Minus z squared. And in the denominator also there is delta x times 1 plus I alpha delta x. But we are dropping delta x square anyway, so you can drop it here. But if you want, you can keep it, but you should, I mean, strictly speaking, you should drop this right here. Because somewhere else you might have dropped it and then now you're keeping it, it may not be consistent. But in this case, I can see that at least algebraically it will go through because z square cancels out, same idea. But strictly speaking, I don't think it's a good idea. Keep it here. In another problem, it may not cancel out. So 2 times z times delta x, 1 plus I alpha delta x, plus delta x squared, 1 plus I delta x. Because why I'm worried there is that you might be having some delta x squared here in a more complicated function. You drop that and you expect it to cancel and it may not cancel out. Right? So this cancellation may not work all the time. Like in this problem, it is clearly canceling out. But in another function, it may not cancel out because it's there somewhere here. Right? So unless you see through that, you will say, oh, it's not working.
And that's
Yeah.
a pattern in higher order terms. that
Correct.
we're gonna-
Yeah, exactly.
Yeah.
Always that will be there. It's just because you dropped it to be consistent, you should drop it here also. So drop it here, drop it everywhere, and then this delta x cancels. Right. So that's a good, good question. Yeah.
Thank you.
Yeah. that should pretty much answer for any path then, right? So now we have seen a quadratic integral for any path. The linear is the strongest one, so keep only the linear. So take any curved form, second order is neglected, so only the linear one survives. So now you have in principle at least thought twice you proved for any path. Yeah. Okay, good question. Yeah. Did I answer, Johnny, your question? You had some concern there.
Okay, in the earlier question, what we did is that also in the last class we did limit del z tends to 0. You use both the imaginary and the real part in the denominator, but we used limit del z. I mean, once the del x tends to 0, and then the del y tends to 0. I mean the one.
Oh yeah. Oh, I see. No, I think that was a misleading comment probably. So what I see your question. So what you're pointing out is that, yeah, I think I made a mistake probably in the. Good. Yeah. Okay. So I think what you're trying to tell me is that yesterday we did, so there is the z, so delta z, we set delta x plus I 0, right?
Yeah.
I 0, and then df by dz was equal to limit delta z tends to 0, and there was z plus delta x plus I 0, right? So whole square minus z square divided by delta z, delta x plus you're suggesting that I told I delta y, but it's I 0 again, right? But this is, see, if we go, I think in the diagram it is better. If we go delta x this way and delta y independently, that's different from going along a curve. And when I go, so my choice is to go along a curve, right? So earlier I was telling only along a line, but now after Ken's question, we can go along a curve, right? If we are going along a curve, delta x and delta y are not independent, right? Delta y is forced to go in a certain pattern based on delta x. That's this curve decides that. So if we are saying it is arbitrary delta x and delta y, yeah, especially in the first when I'm defining the derivative, right? It's okay to do that. But there is a slight difference, and I see your question. Yeah, good point actually. I don't know the answer. Okay. Like what is it different? Like delta x not being equal to delta y coming independently is a stronger statement than coming on a curve. Right? Delta x being independent of delta y, and I think analytic function obeys that. Okay, so you're correct that I can be independent. Delta x is independent of delta y. That's one way of approaching a point. Anyway, first I go delta x and then independently I come delta y. I think that's okay. But this is slightly different. This is we are coming along a curve, very specific curve. So delta y is decided by delta x. And let me leave that open. Let me not answer that. I don't know. My guess is that an analytic function does not care whether I'm coming along a curve or not. Any way you come, that's okay. Delta x, delta y arbitrarily come, that should be okay. It doesn't have one along. Okay. Yeah. So yeah, I'm confused a little. Yeah, but let's for now let's accept that it is arbitrary okay. But I'm a little concerned about that. Yeah.
Thank you.
Yeah, if you had asked me independently in a different context, I would have said, yeah, that's perfectly fine. But now that I see that, oh, this is actually a long path, then I'm little, those two are different statements. Worry. Okay. Good point. Okay, so with that caveat, with that not understanding completely there, without answering your question, suppose I proceed further, it might show up again here. All these are connected. So yeah, keep your thoughts open and ask me again if I think all these are connected. So okay, so now we have done differentiation. So next is as you do in analysis, integration, right? If there is a differentiation possible, there must be an inverse of that. Let's do differentiation. So how do we do integration, a complex integration now? So we want to do and yeah, let's go back in a different context altogether. And just so that you have an analogy, I think it is all very similar. So I like to bring in an analogy. What is a conservative force? This is Newtonian physics.
It's independent of the path I am taking.
Correct. Good. Very good. And
it can be expressed as a gradient of a vector.
Very good. Yeah. Give an example of a conservative force.
Equal to minus del V.
Yeah, but give an example, very real force.
Electric field can be expressed as
electric field.
Yeah.
Yeah. I heard electric. Yeah. Electric field, very good. Yeah, so electric force.
Yeah, electric force.
So electrostatic force
can be expressed as a gradient of the potential.
Very good. So that's a conservative force. Any other force? Momentum. No, force. I'm talking about force. A real. Like, what are the forces? Like, can you list any forces that you come across? Tell me what are the forces that you can think of? All the forces.
Kinetic and
force. No.
Magnetic
force. Electric force. What else?
Gravitational force.
Gravitational force. Third. Yeah. Strong force. Let's keep it aside a little. Let's do it one. I mean, yeah, strong. You say strong interaction. Yeah, let's keep it away because we haven't seen that yet. Coulomb force is electrostatic force. He said that. Yeah. So 3. Only 3. Huh? I can list it here. Yeah. So gravity, like gravitational. You said.
Yeah.
I want everything like gravitational, electrostatic. You said. And you said electric, but I made it electrostatic.
Yeah.
Then there is magnetic. You said, I don't know what that means. Maybe we'll see, look into that. Right? Magnetostatic, maybe. And you know the next question that is coming, right? Are all this conservative or not? But that's okay. Only 3 forces? Oh, yeah. You're doing Newtonian physics for many years. More forces you've seen.
Rotational force.
Rotational force. Make it more specific. Okay, how do we define force? How about that? I mean, I was talking to my nephew today morning, right? And he asked me what's a force. So I was trying to explain what a force is. It's very difficult. What's a force? How do you define it?
Mass times acceleration.
What is mass? Like, this is what I do in my introductory level physics class. I say that we won't define a mass and a force. Force is whatever intuitively you think of when you're pushing. I don't know a better definition.
Change in pressure. I mean,
what is pressure now? I don't know. Like, I was thinking of, I was really motivated to go and look into actual Newton's work. Like, how did he come up? Like, how did he explain? Like, he was explaining to the people who are very critical. No one wanted to believe at that time that this is all true. So somewhere he cannot hand wave it, right? That force is something that you feel when you're pushing. I don't know what he did. I don't think mathematically it is a very clear definition is there. That's quiz. Give me a proper, honest, be honest to yourself and pretend that you are in the original days of Newton and you're trying to explain to the, let's say, a very critical audience as to what force is, right? And force and mass, like acceleration. So that is one equation, F is equal to ma. So you can, third one, you can define it as force over mass. So what is force, what is mass? When I teach, I say that this is just intuition. Mass is anything that occupies space. I just hand wave it. And another is time I struggle with. The very first class in physics, introductory physics course, you have to define time, right? Kinematics comes in. So time, how do you define time when you have nothing in it?
I think defining time is the hardest of all those.
Probably, yeah, agree. So that's your quiz, okay? But irrespective of that, once we cross that, the moment you cross that stage, then you can have force, it's defined. So then you start talking about forces. And then you introduce a lot of forces, right? Even though the basic definition is not that, we introduce a lot of forces. So what are the forces you do in Newtonian physics? Normal force? Is that a force?
True. Yeah.
Normal force? So anything that's independent of this? Normal force? Anything else? Force of time, when you have a rope attached to it, force of tension.
Yeah, tension.
Tension, force of tension. And then there's friction.
Yeah.
At least the contact friction. Standard Coulomb friction, not the air resistance, not the drag force. Drag force, I think, is probably more fundamental. This is the contact, the Coulomb friction, or contact friction. What else?
Spring.
Spring, yeah. That's nice. Spring. And that's it. Our list is that small.
Centripetal, gravitational.
Okay, yeah. So that's what I was actually telling. Yeah, I was explaining to my nephew. So the best I could come up with, the force is always by an object on an object. Right? That's probably correct, right? I cannot exert a force on myself. Probably that's correct. Every force you think of is from one to the other. Now I ask centripetal, who is exerting that force? It's not, right? That's not a force, right? Then you do say that that's a pseudo force and all that. So centripetal is not a force. That's it. What else?
Force due to a web, but what is the name of this?
Force due to
Web.
web. What? Web?
I mean, any waves actually exert a force on a particular particle when it goes to the medium.
Energy.
You mean, I think surface tension? Oh, I didn't get web. Did you say WEB?
WAV.
It sounds like
Force due to
Oh, wave. Oh, yeah. Good. Okay. That's I think that he was saying pressure there, right? So that's something like that. Like it is, very good. But let's stick to Newtonian physics. That is going into a field concept, like into the idea of like electric field, for example. Like force is the gradient of force is the charge times electric field. But there is if you want, a concept of field coming in. Okay, good point. But let's, like atmospheric pressure, all that is related. Yes, good point. Yeah, it's a little harder. I can keep it. I can keep it. But like, and it seems like it is a small list, right? I mean, but there are many of them. Like you can actually, these are all empirical, right? Especially when you introduce normal, tension, friction, they're all empirical. Like you kind of get into a new regime. Like for example, how does a addition force, if you're in a fluid, that is as you were saying, like that is a repulsive force you can think of. So there's plenty of them, and in a contextual thing, you do talk about it. But now tell me, so why I listed this is that is this a conservative force, gravitational force? It was a good idea that you said this is conservative, right? Because you had a very good argument that this is the gradient of a potential, right? And apparently that's a way to think of it as conservative. That's what I want to highlight here, because there's a one-to-one correspondence with complex analytic functions and this conservative forces. So the question is, can you write gravitational force as a gradient of a potential?
Most probably not. But yeah. It doesn't matter where I am, but the gravitational acceleration will be G. So it's dependent on the.
So what's the potential? What's the gravitational potential? Give me a function whose derivative is the Newton's force.
Gravitational potential is negative.
Negative?
Yes.
To mumble. You start and then you go down. Yeah. Like people complain about me also. I used to mumble a lot at her when I was
Yeah,
young.
but see,
Say that again?
I'm not sure that
Yeah,
gravitational potential is sometimes it is negative or it is negative.
yeah, that's correct. What you're saying. But my question is, okay, gravitational force F, right? Gravitational. What is the gravitational force?
mg.
GM
No.
D square.
That's too late. Sorry, but at this stage we cannot say that.
Big G.
Yeah, big G mm, right? Yeah. Yeah. That's the same thing, but sorry. Okay, so and there is a vector, right?
Yes.
And if you say this is on one due to the other, there's sometimes a negative sign of it. It matters on which mass you're talking about. So we are saying, my question is, if I can write this force as a gradient of something, negative gradient of something, then it's okay. So can you think of a potential whose derivative is this? Yes or no?
No.
No. Say no.
I mean, I don't know. Maybe.
You don't know. Okay. But John, it's surprising because you yourself said that what is electrostatic force? Tell me.
QE.
1 by 4 pi E0.
QE.
Yeah, 1/4 pi epsilon naught
Q1,
Q1,
Q1, Q2.
Q2 over R square and R hat, right?
Yeah.
And then I say, can I write a gradient of this? And you said yes. Right? That's mathematically identical. Right? So now I again ask, what is phi here? What's the gravitational potential? What is the electric potential here? Phi, I think I'm going. What is the electric potential? Phi. Derivative of what is this?
T by R. 1 by 4 pi E0.
1 by 4 pi epsilon naught Q1 Q2
Yeah.
by R, right? And if you do this derivative, you'll get that. Like you can almost see this derivative. This is in spherical polar coordinates, there's only 1 over R. This is spherically symmetric potential. 1 over derivative of 1 over R is minus 1 over R square. Then there is a negative sign there. That's it. And the gradient of R is R hat. Right? We have seen that in one of the homework. Right?
Yeah.
So that's this. What's the gravitational potential?
If considering the upper one, it's maybe GM divided by 1 by R.
Right, that's it. Have you seen this? And there's a negative sign.
Yeah.
That's because it's attractive. That's two positive charges are repulsive.
It seems now it seems like I have seen it.
Yeah, it should. Right? You seen this, correct?
Yeah.
You have, yeah, I mean, you must have. I mean, you might not be remembering it. Right? You must have seen
Yeah, I
it.
have seen it.
Yeah. Okay,
Mm.
fair. So, is in this sense of asking, is gravitational force conservative? Yes,
If you can express like this, obviously it is conservative.
then it is. Right, that's a simple idea, and I'll tell you in a minute. I'll explain more as to why that's conservative. At least I have convinced you that there is a potential associated with it.
Mhm.
Okay, reasonable?
Yeah.
Okay. So this is conservative, that's conservative. What about magnetostatic? Let's not even go there. We'll come back. So, I mean, in your E&M class, explore that. That's a little harder, okay? Because this gradient, what is then the immediate question of what is phi, right? So it's a little tricky. It's a vector potential, just for your hint. It's a vector potential. You don't have a normal force. But what about normal force? This is more instructive in this context that we're talking about. Normal force, what's the potential? Or actually, this is not potential, right? This is not potential, right? This is potential energy, right? Maybe I should use, like in E&M, we use phi for potential, right? So this is U, let's say. Is this clear what I'm saying? Potential is per unit charge. The electric potential is the per unit charge. So this is a potential energy. Right? Correct. So now the question is, what is the potential energy associated with gravity? Well, that's this, he said, and often it is just mgz, right? If you're on the surface of the earth, then R doesn't change much, then you will write it as a series, and then it is mgz, correct? Potential energy on the surface of earth. In a more general scenario, this is a correct one, correct? Now, what's the potential energy associated with the normal force, or for that matter, tension force, friction, and spring?
So about spring, if equal to minus kx, I can remember
Right.
that.
Yeah, so here U is equal to kx
Kx
squared.
squared. Yeah.
Right. Good. Right, that's it. Good point. What about this normal force? Potential energy?
How to express normal force? I mean, we actually associate normal force with any other force, then we consider this is normal direction.
Yeah, but it's a force, right?
Yeah.
So it's perpendicular to that, perpendicular to the surface, it's a normal force. And first the question is, what's the gradient? The gradient of what? And then you immediately know. Okay. Answer is that there is no potential energy associated with normal force.
Yeah.
You cannot. It's not a conservative force. Normal force is not a conservative force. Tension force is not a conservative force. Friction is not a conservative force. There are very few conservative forces around. If it's a conservative force, it means that it becomes almost a fundamental force. Like when we say there are fundamental forces of gravity, electromagnetism, you said weak force and strong force. What that means is that we can associate an energy associated with that force. Like force is the negative gradient of energy that's applicable only for certain systems, mostly non-dissipative systems. If it's a dissipative system, then we cannot associate an energy with it. Thermodynamics then thermodynamics comes in, all those issues comes in. So that's why thermodynamics is hard. Because here, energy and force is identical in a sense that once you know energy, you know force. And system tries to reduce its energy. System is trying to attain minimum energy. And force is what we see it while the system is trying to do that. We think, oh, something is trying to pull it. So that's our more imagination, but system, or at least one can imagine that energy being minimized is probably a nicer way of looking at it, but it's one to the other. It's always what is more fundamental, we don't know, right? But energy is trying to be minimized, and force is a manifestation of that process, negative gradient of that. Remember, derivative is that minimum part, right? Okay, so all this, so let's go back and formalize this a little. How come the gradient is coming out? And then somewhere you guys said path independent, right? How do we connect all this? So let's put this all together. Or at least let me state it. Okay, so once you have a force, we can talk about a work done by a force. Right? The work done by a force, what is the definition of the work done by a force?
Distance.
F dot S, I think.
Distance.
F dot S along, yeah, F dot S, but if it is not a uniform force, then you would say it is dl. That's your S, right? Small displacement dotted with force, right? Anything else you want to add to this? Is that a well-defined limit? Yes, good. So you want to go from initial position, our initial, to our final. Right, so our imagination is, actually I don't even want to draw this axis. Right, so there is our initial, and there is an our final, and dl dotted with f. Is that a well-defined definition of work?
This is the angle.
Angle
Angle,
will come if we use the
Cos
dot product, cos theta, sin theta.
yeah, but what do you mean by angle? Explain. Maybe you're thinking in the right direction, but explain to me. So I said,
Force.
so there is some particle going from initial point to the final point, right? And there is a force acting on this. And this is the work done by the force, not by my hand, not by my, not done when I'm walking. It's done by a force. So work done by a force, right? Usually we say the work done by gravity. So the work done by a force, right? So, and I'm saying this is not a complete good definition because tell me what this means, right? So I'm going from here to there. What is missing now?
Direction of force.
Direction of force. But I said force is given to me at every point. Let's say it is uniform. Okay? Let's say if maybe that's the confusion. Let's say F is equal to minus Z hat times mg. So simple standard, simple force. Right? But I say that, how do I calculate the work done now? Tell me. From our initial to our final, I'm going. Is that a unambiguous definition? Is the question clear? Or I'm trying to say that that's not complete definition. What is missing? In the definition of force, can you imagine?
A summation, maybe?
Summation, yeah, that's the integral.
Oh, yeah,
Right?
right.
Yeah,
Okay.
that's good. So that is a breaking up now, right? A break this, going from here to there, break it up into small pieces. Yeah, that's a good part. So what is DL? Small length. Show me. Where is it? Is it this? Or is it this? Did I specify that?
The shortest.
Shortest. Do we say that? If you remember your definition of work, do we say that it's the shortest part? Do we say that? Maybe. Remember your definition of work done. Do we say that it's going from our initial to our final? Do we say that it's going along the shortest part?
I think it matters.
It doesn't matter. That's a new thing you're bringing in.
I don't think it matters.
I think the angle between the DL, the small part I am considering in the force.
Angle
I mean the angle between the force
and the
direction.
DL.
DL, yeah.
Yes, that's correct. But where is DL? If I want that angle, I need DL to begin with, right? Which is DL has to do with, I'm going from here to there. It's a path. Stop at a point for a moment and decide where you're going, right? And Ken said that, no, you go along the shortest path. Is that correct? Is the definition of work involving shortest path in this case probably is this? Does my definition say that? And then Sen also said that no, probably it doesn't matter. Does it matter how you do the work, how you go along? So suppose that's one path, and that's another path, right?
As it is a conservative force, it's only dependent on the
Yeah.
initial and final one.
So that's so many things coming up. So actually, this definition is not precise. You have to specify a path. Often there is not so much space, typographic space there. So often it is said in words. Like every time you give a definition, it is said in words that, oh, this depends on the path. But it's good to say that work done is comma, you have to specify a path. For different paths, the work done is different. So there are many paths possible. Give me a path, that's an arbitrary path. And if you change the path, work done is different. In general, different. Okay. In general, very different, but there are very special forces for which it is path independent. That's a conservative force. Okay, is that clear? And then the question comes, give me an example of a conservative force. We'll talk about that, right? Think of analytic function again. This is very much that now we are going to connect it directly with that. Okay, so not all forces are conservative. Not all functions are analytic. It's a very constrained system. So now, let's say, I try to convince you that in the definition of work there is a path dependent. Let's say it's independent of the path. Okay? So if it is independent of the path, like if it is path independent, what can you conclude after that? So just logically speaking, that means that work is equal to, this whole thing doesn't care for how I go. I can go to all the way to another galaxy and come back. So it depends on only some function here, the u of r final minus u initial. That must be correct, right? It doesn't care for in between. Right? That's not very obvious, but if it depends only on the final and initial, it doesn't depend on the path. This must be true. Okay. If that is the case, then let's just for notational purposes, let's say this is minus and this is plus. Actually, let me write it as this. That's just the way it is. Okay, that's how it was defined. Okay. If that is the case, now go back to your integral. Integral of what is actually giving you this kind of feature? So you would say that if you think of it, if it was one dimensional, let's say, dx times d by dx of u, right? Dx cancels out. It depends only on the final and initial. Correct? So integral of a derivative, right? That's what is happening when it is path independent. It's all canceling out things whenever you return back. It's like an integration, right? If you go up to the right and then come back to the left, I subtract back everything. Like one dimension is very obvious, right? So, but now what's the more generic process of a derivative? This is dl dotted with gradient of a function. Right? These two cancel out each other like exactly like one dimensional. And that's our initial, that's our final. This is equal to this, right? You can write this as plus u if you want, but by notation, like we always write it as minus of the. So work done is the change, minus of the change in potential energy. And this is defined as a potential energy. Potential energy is possible. It's possible to define a potential energy only if the force work done is path independent. Okay. But then you say that, okay, so which means that this is basically what I'm saying is this is minus delta U, right? When does that happen? If this is true, there is something else you can say in vector calculus. or actually it's not this, right? Sorry, yeah, if you can, so this is all equality sign, right? This is equal to this, right? Minus delta U. Which depends only on final and initial. Then you can think of some vector calculus theorem. Think of magnetism. What is Ampere's law? Or maybe I should state this better. Okay, hold on. Give me a second. Sorry. Maybe I should state it better. Okay. No, one more step. I'm going ahead of myself. Yeah. So this is correct. Yeah, we should just keep going in this way, right? This is correct. Now, if this is true, what if I have initial and final point the same? That means I make a loop, right?
Closed loop.
So this means that a closed loop, which I will represent like this, like it's a three-dimensional space, I'm making a closed loop of dl dotted with f is equal to 0. Now tell me if the closed loop of a vector field or a vector function, right, dotted with dl is 0, what can I say about f? That is, in vector calculus, there is a theorem. What is divergence theorem?
Yeah, divergence.
No, what is divergence theorem first? It's not divergence theorem.
So I can express the dot product as a divergence of the vector field.
No, you're getting carried away. What is divergence theorem? First for me. What is divergence theorem? So divergence theorem deals with the volume, right? Volume of a divergence of a vector field, let's say E, a vector field is equal to, now this is the theorem. This is Gauss's law. Okay. This is your charge. Integration of charge. What is Gauss's law?
E dot
E dot
So dA, very good. Right. So this is dA dotted with E. So this kind of cancels out. This is exactly like the derivative that I canceled out, right? There is a derivative. There are three integrals. The volume integral dx, dy, dz. One of the derivative cancels out. Remaining is an area. Right? Something is missing in this. Closed loop, right? It's necessary that it's closed loop because it's at the boundary, right? After you cancel out, it's only at the boundary. But this is now a volume integral. The boundary of a volume is a surface, right? So that's a surface, right? Now, similarly, this is not this. Okay? This is a dl. This is an area, right? This is 2 dx dy. There is only one dx, right? So what's this in this context? There is another theorem. This is divergence theorem. What's the other theorem in vector calculus? There are two very fundamental theorems. Surface is the boundary of a volume. What's the other one you can think of in that spirit? Huh? So
the boundary of the surface.
Boundary of a surface is a curve, right? So do the same thing here now. Boundary of a surface is a curve, correct? So boundary of a surface, let's say dA, right? And is a curve. Curve has to be complete because it's a boundary. So that's dl. This is the boundary of this. What comes in here now? This divergence theorem.
Stokes theorem.
Stokes theorem. What is that? Correct. Very good. That's called the Stokes theorem or the theorem of curl. It's divergence curl. So it's a curl that comes in. Crossed with, usually we say B because this is the Ampere's law, right? Dotted with B. Right? Ampere's law is if you go magnetic field, if you go in loops, that's equivalent to the curl of the magnetic field, which is the current, right? So this will right side. But here there is a charge. This is Gauss's law. Like on the surface, This is equal to the total charge inside of the loop. Here, this is the total current, del cross B Maxwell's equation, if you think of it as a current. So this is the current, right? So surface, boundary of a surface is this. Now connect this with this. I said we are talking about forces now, right? No magnetic field, nothing. This is forces, right? Different context altogether. We are saying that the work done by a force is zero in a loop, any loop, right? That means this is zero. If this is zero, that's zero. What can you say?
Constant.
No, something is zero, so that means curl of the force is zero. Correct. So this implies that curl of the force is zero. Okay, so conservative force has three definitions, if you want, three implications, one-to-one, right? One is that it can be written as a gradient. Somewhere we said that, this one. It can be written as a gradient. That was somewhere here, right? This to this. Is independent of the path. That's another property. And the third is the curl of the force is zero. Like if you take the curl of this force, quiz, right? Take the curl of the gravitational force or the electric force and show that that is actually equal to zero. It has to be zero. If it is not, if you're not able to show it, something is wrong in the mathematics. Like that's the way Einstein would have done. Like he believed in the physical principle so much that mathematics must be wrong. I mean, it's a loose statement I'm making, but there's some merit to that. Okay, so 3 points, correct? Now let's go back to our complex function. All this was a practice, so 15 minutes, 10 minutes remaining. Okay, so let's go back and any questions here, comments?
Yes. Just one. So like the force being in the top right, that example.
Yeah,
The force being negative mg, that means it is path independent.
it turns out to be yes.
Because
It is not very obvious right away,
right.
best thing is that you take the curl, like curl of this, like, and it will come out to be because that is a, yeah, it is constant, so it will be,
Right,
yes, yeah. It will be, yeah.
That was okay. Thank you.
Correct. Yeah, it is curl is independent, and is that straightforward? So every constant force will be a conserved force. Then the question comes: normal force, is it constant or not? But right, there is always a boundary there. A normal force. It is a constant, often a constant, but not necessarily. At some point, it kind of breaks. The moment it loses contact.
Depends on the system.
Depends on the system. So, yeah. Quiz again. Is every constant force if the force is a constant, can you define a potential energy for that? Okay.
Is every constant force?
Is every constant force a conservative force? Is a constant force a conservative force? I think yes. Yeah, it seems like it is. Yeah, okay, I think so. But to criticize it, come up with a counterexample. Or the question is, what about the normal force? Argue what is happening with normal force. Okay. Yeah, good question. Yeah. Any other comments?
So
Yeah.
So in a conservative force, there will be no rotation as the curl is zero.
Rotation has to do with R cross F, right? Curl of F is now a field. Like now, curl of F, if you want to imagine it, the force field is, for example, for gravity. I should do this here so that video also have it. Hard to follow. Okay. So here, so if you were to plot this, at this point, you have a force here. Right? At this point, you have a force here. At this point, you have a force here. Very quickly, you run out of ideas how to represent a force at every point, position-dependent forces. So this is one way of representing this information about the force. You call it a field. So these are field lines, not the electric field lines, these are force field lines, right? And then you see that, oh, these are all coming out of a point. When it comes out of a point, that means at this point, not necessarily everywhere, at this point, the divergence is not zero. But now you can think of forces of this kind, where the field is like this. Is that clear what I'm doing? So the force field is like this. That means if you put a charge or let's say object here, it experiences a force in this direction. It will tend to move in that direction if you start from that rest. If that is there, that means the curl of the force is not zero, right? That's what it means. So then you don't have to be conservative. It also means that if you were to think of a fan blade, like just a turbine, if you were to keep a turbine, a point turbine in principle at some point, and you ask, will it rotate or not? Like in this field, if I were to keep a turbine here, will it rotate?
No.
No, right? Because there is a blade here. I think of this as a turbine. This will experience a force this side. If it is uniformly distributed, this will experience a force this side. So it won't rotate, right? Like especially if that object doesn't have any structure. So we are saying point object. It shouldn't have any directional sense of its own. But if the turbine rotates, then it has a curl. Think of a water and you put a turbine. If it is rotating, that means it has a curl. Like it's not there. So you do have curl. It is there in nature. You have a lot of curl, but that means that it is not conservative force. And the moment it's not a conservative force, it is not that it doesn't. It is not a good system. It's just that we don't understand it. Our understanding is very limited, and it's 400 years of work, but still it's very limited. We don't understand turbulence. And turbulence are these kind of motions. Like when you think of a water dropping from your sink faucet, you don't understand it very well. Like if it is very smoothly flowing, we do understand it. But you know what I'm saying, right? When the water is flowing, there is a smooth flow where everything is fine. Water doesn't go off from the stream. But sometimes there is a whitish structure that shows up. That's a signature of turbulence. We pretty much don't understand. It's probably an overstatement, but our understanding is very limited when it comes to turbulence. So yeah, and that's because of these kind of issues. We don't understand the moment we don't have an energy, or it's very easy when then it's an energy associated. There's a lot of work to do. Yeah. But still, we have made a lot of progress, no doubt. So did I answer your question? Yeah. So your question was, curl of F is that, so this is how it will look like. And one way to imagine it is that, you have a turbine and will it rotate or not? And it does rotate, right? Our electricity comes from the turbine. So there are such forces. It's just that we don't understand.
Okay. Thank you.
Yeah. Okay. Good. Okay. All that lengthy digression, but I think it's useful digression because it's a very fundamental concept. So I think I don't mind the digression, but it comes at the price of your homework getting postponed, but we'll try to go far. Okay, so now let's go back and let's define a gradient as just a two-dimensional gradient. And it's, let me write it in this form. X and d by dy. And just writing it so that I don't give you an indication of, I'm writing it as a comma, because in this way of saying, I haven't said it's whether it's a vector space or is it a complex form, right? It could be a complex line also. That's purposely done. And let's say there is another, let's say F, which is a vector, right? Which is U and V, right? Which are functions of X and Y. U and V are functions of X and Y. And now tell me, and I also give you the fact that du by dx is equal to dv by dy, and du by dy is equal to minus dv by dx. That's it. Set of, so these are three definitions. And now tell me, what is del cross F? Can you calculate that very quickly? Probably, since you're doing the cross, probably you need a third one, right? Cross is not defined in the two dimensions. Let's put a third dimension. Use the determinant. If you're familiar with the determinant rule, you can use that if you want.
dv by dx minus du by dx.
And what is that? Yeah.
I could del v by del x minus del u by del y.
Del u by del x and del u by del y, right? But that's equal.
Equals.
Or am I missing something? Oh, maybe. Yeah. Okay. I think I'm getting confused here. Okay. So what would you say? So yeah, maybe you guys are correct. Yeah, you cannot do anything further, right? Yeah, maybe I overdid it, right? So yeah. Okay. Let me leave that here. So that's a vector, right? Yeah, what did you get? Tell me. So this is ijk. Yeah, I overdid it.
Okay.
Y0 u 0. And that's equal to k times, yeah, k hat. So this is okay, right? Maybe I'm not overdoing it. K hat times
dv by
Del v by
dx.
del x minus
del v by del x
del u.
by del y. And what's that? Del v by del x. That is del v by del x. Yeah, right?
Second one.
And
Minus 2.
it's minus. What's missing? Yeah. Why is it not going to 0? Did I write this correct? du by dx is dv by dy. Du by dy is minus dv by dx. Correct? So dv by dx is.
Yes, yeah.
Is it 0? I want it to be 0, yes, but it's not 0, right?
It's not 0.
Oh,
I want it to be 0. Why is it not? That's because okay, this is in a real plane, right? You're doing this in a vector space, right? In a complex function that is I there, right? So let's try this, okay? So let's hope this works, okay? So this is not 0, right? Okay, good. This is probably not there. I mean, I think I expected it to be 0 the way I constructed it, but let's not. But that's not 0. So in vector space, del cross F is not 0 the way it's written. But now let's say del is no, I have to say what is gradient, right? Yeah, so let's say d by dz sorry. Yeah. So let's say d. So this is so now f is equal to u plus iv, and z is equal to x plus iy. Right? And let me also say that this is given d. The same conditions. d by dy. Oh, you guys are getting late. Right? That's the class. du by dy is equal to minus dv by dx. And let me tell, what about I want to construct a curve. Sorry. Okay, I don't know. Okay, let's stop it. We'll come back to this. Maybe our quiz, right? What's the similarity in here so that it goes to 0? And the idea is that if it goes to 0, then you can use all those properties, right? Then it's a path independent, and that's immediately Cauchy's theorem. And that's the key to all contour integrals. But we'll come back to that. I would love to do that, finish that, but I think you guys are better. I shouldn't keep it.
Is it a question of basis?
Because there is an I haven't taken. So here is the conclusion. Here is the conclusion. This will come out for an analytic function. dz f of z is equal to 0. If I have a complex plane, an analytic function, only if it is analytic, everywhere on that plane, and I go along a contour, but it's independent of the path, so I don't have to specify. Same thing with that path. It's independent of the path. If I go around and come back, that's equal to 0 for a complex analytic function, which means that there must be a curl feature to it. And it is there. It's just that the way I built it, I'm not able to see it. Okay. So there is a curl feature to that. That's basically Cauchy. So this is the curl definition if you want, right? But you want to specify more clearly. Remember, there is an I in complex numbers. That's the difference between the vector space and complex numbers. So we want to say that more clearly. So did I give the idea? So this is what you're going to be aiming for. This is called Cauchy's theorem. Everything in complex numbers is Cauchy. Right? Our Venn diagram came and he within 25 years solved everything in complex numbers. He didn't leave anything for others. Sorry, I would have loved to finish it, but I think you guys have a class now, right? Am I right? I think I couldn't keep you guys putting you and hanging, but maybe that make you guys read and think of it. Read. Yeah.
Thank you.
Yeah, I'm good. Yeah.
Do you think that even like black holes have conservative gravity?
Oh, yes, that gravity is, okay. Hold on.
Because yeah, like
Okay,
It's
now
nothing really.
what happens is that the Newtonian gravity is conservative. Okay. Now what happens is that what Einstein basically did is that the way Newtonian physics is done, it's all that is just a force. Like you don't talk in terms of electric field so much. Or in electrodynamics, you talk about electric field.
yeah,
Correct.
Yeah.
Newton doesn't do that. Newton just has a force.
Mm.
There are two objects as a force.
Mm.
But what Einstein did is that there is a field.
There's
There is a gravitational field which has momentum and energy.
I see.
So that leads to the idea that just because sun exists, it doesn't matter whether Earth is there or not. It has an energy spread out everywhere around. And that makes it a tensor field.
And so it's not.
It is conservative, it is hard to do. Most probably it is conservative. The way we understand it is most probably conservative, right?
Interesting.
But it is so hard because the energy now spreads all the way to infinity. So when you say sun, it's
Right.
not an object which is confined in its own space. It is spread. Its field, its energy is distributed everywhere. And that's hard to capture when you do an integral. What we are saying is, or it's not that mathematically hard, conceptually hard in the sense that what do we mean by the energy is conserved when energy is all the way out there? So there's a lot of issues that comes up with that. And the current understanding is that there is energy even at very large distance, significant amount of
Interesting.
So yeah, so it is no more a vector field. Gravity is actually a tensor field, the way Einstein puts it. But when Newton said it, it's a vector field.
I see.
The way Einstein put it, it became a tensor field.
Oh.
And if you want one more step, electric field, if you think, what is the source of electric field? If you want to create an electric field, you put a charge.
Right.
Right? If there is a charge, electric field comes with it. Right? Charge, electric field is spread out everywhere, whatever I'm saying. Now you ask the question, what is the source of gravitational field? And that happens to be energy and momentum. And mass is also one
Right,
piece.
right.
But Newton could see only the mass part of it. Einstein said that anything that has an energy will contribute to gravity. Like photon gets attracted to the mass.
Right.
Just because of the energy. That's a very nice idea.
I'm gonna look more into it.
Yeah, on the right side of your Gauss's law is energy momentum. On the left side is Einstein's gravity,
Right.
which is it written in terms of, you interpret it as curvature of space. Yeah, I can tell this more, but you should run.
Right.
Yeah, okay.
Thank you, Doctor.
Yeah. Mhm.